All right, so let's get started today. We're going to talk about the overview of concrete and concrete materials, a little history about cement and the evolution of cement and concrete over the years. So to begin, one of the oldest concrete and cement type uh, structures in the world has been found over in what the area currently of Israel is. There was actually a concrete floor that was found there back in the 80s, like you can see over here in the right-hand picture. And the problem that concrete back then had was actually made really with like a quicklime. It was kind of like a non-hydraulic cement, meaning non-hydraulic is not hard with water, so it's not it's soluble, so water soluble. So in essence, if you poured a concrete, if you think about concrete today and you poured concrete, you let it hard, well, even if it was as old as this, 9,000 plus years old, it wouldn't matter, because if you put water on top of it and you started trying to maybe start scratching the top of the surface, eventually that would that concrete, that cement would start wearing down, and over time it would actually turn into that paste, that flowable paste that you'd think of. So it's not like concrete today where it just hardens and it's not soluble in water. So there's a big difference between the cement, a non-hydraulic cement, and a hydraulic cement. Probably some of the more famous structures that have been built out of cements or sand mortars, gypsum, plaster of Paris, stuff like that, was in Egypt. But the pyramids, they built all sorts of stuff over in Egypt, with quicklime, the same non-hydraulic cement that we just talked about. The Romans actually got a little more creative. They figured out the issue with the water, and they were actually able to make a non-soluble, so non-hydraulic, a hydraulic cement. And it was kind of cool how they did it, where they actually realized when they looked at the volcanoes and these different lava layers came out. Some of them would be what you think of with like lightweight aggregate, some of the layers. You go out and you grill a steak with your grill, and maybe you have those little bitty lava rocks that you're using to grill with. Actually, they look very similar. Very similar to stuff like lightweight aggregate. Some layers were like that. Some were more of like a fly ash that you'd think of here. And there's some that may actually have been a more of like hydraulic based cement. But what the Romans found out was, if you took some of this quicklime, so the cement that's not, that's soluble in water, and you took some of this volcanic ash that they had, and then you heated everything up, you could actually make a cement with it, a hydraulic cement that didn't have all these water issues. So it was really cool. And one of the best places for volcanic ash was in Pozzola, Italy. That's actually where the origin of pozzolans came from. So in this class, you might hear secondary cementitious material. You hear the word fly ash a lot. And, people associate the word pozzolan with maybe like a class F fly ash is a pozzolan. And what that is in essence, it's very similar to what you think of it with a cement, how it looks anyways, but chemically it reacts differently. So it reacts at a much lower rate, and you're able to replace a certain amount of Portland cement with say a fly ash. So these are commonly at 10 to 30% for fly ash. and they actually can enhance the performance of your concrete. So just kind of a side note, we'll talk a little bit more about secondary cementitious materials and fly ash and pozzolans coming up, but I just kind of wanted to throw that out there just in case you were kind of familiar already with what pozzolans were. So the Romans, they took this cement, this hydraulic cement, and they made all sorts of different concrete structures all over the world. And the word concrete is actually derived from the Latin root word concretus, meaning compounded or hardened, put together. And so they built a lot of different structures. Some are actually still standing today. There's a lot that they built that didn't do very good, and they're no longer here. But the ones that were really good, the ones that had the best materials, the best craftsmanship, they're still around. You know, the best design too. So, you know, all three of those: craftsmanship, design, and the actual, you know, using the right materials. You'll actually find with most engineering, that's actually what happens. So if you want to have the best structures, you better have good engineering designs. You better select and use the right materials. And when you're building a structure, you need to have a minimum, you know, quality of work. And you know, and these structures will last a long time. So unfortunately, the Romans figured out all sorts of different things, but they actually, you know, they had the fall of the Roman Empire, and they actually lost a lot of really good information, a lot of good resources. And so, you know, then you had the Dark Ages that kind of came in, and nothing really happened with cement, with concrete. Neither one of them really advanced much. It wasn't until the 1700s with John Smeaton where things really started progressing. You see, in England, you know, it's on an island, and the shipping from all over the world was a big deal back then. And they really needed to figure out how not to ruin their boats, because you get too close to the shoreline and you're going to wreck your boat. And so you put lighthouses to kind of say, hey, you're pretty close to the shoreline. You need to be cautious. It's right here. But these lighthouses didn't last very long in these very corrosive seawaters. So what John Smeaton did was he started investigating lime properties, started really looking at what exactly would be the best building material to use on these light towers. You know, wood didn't really work, steel wasn't really work, or metal, I should say, didn't really work too well. But you know, there seemed to be something with the lime. And really, he started doing so much research and looking at stuff that he actually brought us back from, you know, to pretty much where the Romans were, with this basics knowledge of hydraulic cement. And it was kind of cool how he brought us there. And, you know, in essence, his big, you know, name to fame was he actually developed this Eddystone lighthouse, which lasted a lot longer than a lot of these other lighthouses. It was built really well, and these ships wouldn't go and crash as much and lose a lot of their cargo. So it saved people a lot of money. Also, I should note that John Smeaton's actually the first. He's what's considered the father of civil engineering, and many different discoveries occurred right after John Smeaton. So Joseph Aspin, just, you know, in the 1800s, he actually was credited for inventing Portland cement. His son and him, they kind of worked together, and then they got in some battles over the years, and they actually split apart. And I think his son actually figured out what, you know, a little bit more of what actually happened, where they could actually have a Portland cement that was like a hydraulic cement that worked really well. Smeaton I don't think did as good of a job with the hydraulic. He was kind of um, he didn't necessarily. I think he figured out a lot of that, but he was kind of at the brink of some of that knowledge. Joseph Aspin kind of came in, and he really was a great marketer. So as you had like an engineer that really dug in and tried to figure out all the different properties, you had Joseph Aspin, who he was not a what you'd think of as like a good engineer. Really understand a lot about material properties. He just kind of did a lot of trial and error and didn't really understand necessarily what he was doing. But one thing that he was really smart at was he realized that this cement that he was able to make, he realized very quickly that it looked like this Portland stone quarry. And what was really cool about this Portland stone quarry over in England, you see over here on the Isle of Portland, they would actually quarry this stone, these big chunks of rock like you see over here on the right. And they would take these big chunks of rock and they would put them on a ship, and they'd ship them all over the world. And it was kind of like prestigious, showed you how rich you were by having this stone, this Portland stone. And a lot of times you'd have people that would go out and chisel different shapes and put all the stones together, and make stuff out of them. And so they looked really rich. And so what Joseph said was, you know what, this Portland cement, it looks, I'm going to call it Portland cement, so that you can literally take just powder. You can add some water with it. You can add some other stuff. You can mix it up, and you can make your own stones in the shapes that you want, which is really a genius marketing. So Joseph Aspin really was he had some great insight when it came to marketing. But I don't think, necessarily he was a genius, cement chemist or materials engineer or anything like that. But he was, I think we could all say that using the name Portland was a really smart marketing tool. And that's kind of how we get it. So when you hear the word Portland cement, that's where it derives from. And we'll talk more about what ASTM C150 and what Portland cement, the 5 different types that there are, coming up. So when we talk about the development of Portland cement, again, after Smead and Aspin, it really started taking off after Aspin, putting in that patent, and people were just like, look, I need to figure out how to make this Portland cement, so that we can just start building structures with it, because this is great. It is not soluble in water. We don't have any issues with the water. We just can make, we can take this powder, we can mold it and make whatever stone structure we kind of want with it. So people were just, trying to figure out how to produce it the best they could. Over in Lehigh Valley, Pennsylvania, was kind of like the place back in the 1870s to make Portland cement. I used to work for Bootsy Unison USA, which had the Hercules plant down in Lehigh Valley. I actually took a trip down there. It was pretty cool seeing a lot of different old cement plants and the ones that are still around. And there were other cement plants like you see over here. I used to work for Alamo Cement Company. And over on the right, this is what it looked like back in the late 1880s, I believe. But this is a vertical kiln that was very, very common back then. This is high tech. And people were just producing and shipping as a wagon, whatever it took, boat, whatever it was, to ship and take and railroad, whatever, and move the cement around all over the United States. And really all over the world. People were making it all over the world. Today, this is what the Alamo cement plant looks like. So this is, high tech, late 1800s Alamo cement plant. This is a modern day Alamo cement plant now. This is worth over 1.2 billion with a B dollars. Their electricity bill per month is over $1 million. So, you know, these cement plants, they produce, they have a high energy demand. They do produce some CO2. I think about 2% of the world's CO2 is from cement in the world. And they are a lot more energy efficient today than they even were 10 years ago. And it's very impressive how people are developing cement. And I'll get into that in another lecture. So in general, just to kind of get some basics in, concrete is made of cement, water, sand, and stone. That is before 1950s, that's kind of what it was made out of. You had your Portland cement, you added some water, some sand, some stone, you mix it all up, and it's called concrete. So in this class, when I use the word aggregate, I'm talking about, you know, the sand, the stone, fine aggregate, coarse aggregate. And then if the word paste is used, that's actually talking about your cement. Maybe if you have, you know, cementitious materials like fly ash, slag, that would also be classified in the paste, and water. So it has to be all the combination of cement, water, at least, and then, you know, you can add in other cementitious materials like fly ash. All right. So you also have, so this is a 1910 concrete truck, and I put that in parentheses because, you know, this is a 1 horsepower concrete truck where you have your buggy. If you look real close, this mixer's on a wagon. It's steam fed, and the mixer's, you know, making concrete and mixing concrete together, and they dump it into a wagon and they move it to, you know, wherever they're going to pour the concrete at. And this is, you know, 1 horsepower concrete truck. This is big high-tech technology for 1910. Then you also have the 1950s. If you move a little further, this is a 5-yard truck. You know, this was big time, and this is actually out of the ACI, out of Geiger Ready Mix. They're from Kansas City area. They're good people, make good concrete. And but this is their 5-yard truck that they have, and it's really cool going in it and seeing it. If you're a big concrete nerd like me, and you're able to have connections where you can actually go and talk to, visit their plant. They have some really cool plants, and they have a lot of really cool things going at what they're doing at their plants. So if you're a big concrete nerd and you're up in the Kansas City area, I would highly suggest to check out their plants and see what they're doing. They do enjoy talking to people that are in the concrete industry. All right, so one thing I want to kind of mention is the 1950s concrete truck. This is actually where most of your concrete standards come from, is, you know, the 30s, 40s, 50s, 60s. It was kind of where most of concrete standards were written. And then over the years, they have been evolving and tweaked and and further developed. And so sometimes it's important to kind of realize where your roots were, because people don't always like change. And sometimes your standards need to be rewritten, because you're not dealing with a 5-yard truck anymore. You're dealing with, you know, maybe a 12-yard truck like you see here. So this truck has 6 axles. This one will actually come down if there's concrete in it, just to provide more balance. And it also helps, you know, with these different axles, whenever the truck's really heavy, it provides more support so that it can legally drive down the road. So there's all sorts of different things when you compare a 3-axle truck to a 6-axle truck. There's a lot of technology that gets changed. And just to clarify, Cement is the gray powder that goes into concrete. Concrete's made up of, like I said, cement, water, rock, sand. And the top picture here is a cement truck. The bottom picture here is a concrete truck. People get those kind of confused, but just remember, cement and concrete are different. Calling a cement sidewalks like, it's like, in essence, like calling a loaf of bread flour. Yeah, there's flour in the bread, but that's actually not the correct term. That's just weird to call, say, hey, can you give me that loaf of flour? And people are going to look at you going, what are you talking about? There's a loaf of bread there, but not flour. And it's the same thing with, like a cement sidewalk. It's a concrete sidewalk. So if you've ever went and ordered concrete and had it batched out, and then you go and you sign the batch ticket, you look at that batch ticket and you say, what in the world are all these numbers? I don't get it. And there, and some of you can kind of figure it out, like the ready mix company and their address, your project address, maybe the purchaser's name, your name if you're purchasing it, the number, the truck number, the ticket number, or maybe the plant that came out of. You may have some type of mixture ID, like 3000 PSI, no air, house slab mix. And you may even have a description if they need a description down there. It's pretty common. They may just have the description in the ID. So instead of saying this is mix 1, they may have the description in that. Like I kind of said, 3000 PSI, no air trained, residential floor slab. You may also see the material information, mix design information, and that's kind of what we're going to focus on, is what all that actually it gets communicated. Then you also have the load time, so when it was actually that concrete was loaded, when it was delivered to the job site, the revolutions, how much that drum, that ready mix truck, how many revolutions that drum turned, and then how much water was actually added to the job site. And then you may have somewhere on the batch ticket, you may have volume. So the total volume. So is it a 12-yard truck, 10-yard truck? 10 yards of concrete in that truck. Was there 12 yards of concrete in that truck, or 6, or a yard? I mean, where is that at? So again, this is kind of where we're going to focus on, is the materials that make up the concrete. So before we get started, when you start looking at weights and volumes on that batch ticket, you kind of get confused real quick, because you really need to understand that concrete is sold by volume. So how many yards of concrete to put into a certain forms. So if you go out for a contractor, he's going to go out and he's going to measure, say he has a sidewalk, he's going to measure the thickness of the sidewalk that he's going to pour, and then he's going to measure the length and then the width of that sidewalk, and then he's going to come up with a volume in yards. So you have to do a little conversion, if you move the thickness from inches to feet, and then you have to convert everything from cubic feet to 1 yard. So there's 27 cubic feet in 1 yard of concrete. Just a little FYI, we'll go through that later on. Very basic 5th grade math. But you're going to order X amount of yards of concrete. So the other part of this is, whenever you're designing the concrete, the engineer is going to design it based on a cubic yard, and then you're going to just multiply. So if you need 10 yards, you're just going to multiply all your batch numbers by 10 to get 10 yards. So for a lot of our labs, we're actually going to be dividing by 27 to take it from a yard to cubic feet. And a lot of our mixes will be, 1.5 cubic feet or 2 cubic feet in a lab. So kind of, recognize that. And we'll go over that here here coming up whenever we need to start making concrete in the lab. Then you also have the weight and volume of the concrete. So whenever you're batching, so sometimes you batch by weight, sometimes you batch by volume. Typically, liquids are going to be batched by volume. So you may batch, say 30 gallons of water. So you may have to convert from pounds to gallons for your mix design. Admixtures, if they're in liquid form, then they're going to be, a certain volume, maybe in ounces. Then you have your weights, like your cement, your fly ash, your coarse aggregate, your fine aggregate will all be by pounds. So you can see here, this front end loader is actually dumping into a hopper with a scale that has the number right there. And then at the bottom of this hopper, there's actually a gate with a scale attached to it. It's actually weighing out how much aggregate's going to need to be loaded. Then there's a conveyor belt here to kind of take up that concrete up to start batching it, whether it's a dry batch or a central batch. So that's kind of how, volume and weights kind of go back and forth. They can be confusing in the beginning, but there is a purpose for why you have volumes and weights on your batch tickets, and they're real important to understand those differences. And we'll go through, especially when we start talking about designing the concrete, we'll go through even more about this concept. So with a batch ticket, you're going to have the material on the left, and then you may have some source information. This is an AASHTO. I do provide the ASTMs also to this. Tomato. The AASHTOs and the ASTMs, the standards for the quality of material, for maybe it's for cement or fly ash or water or whatever it is, there's a standard for each of these materials. And it's important to realize that, and we'll go through that in coming up. So for cement, it could be ASTM C150 or it can be AASHTO M85. Either one, they pretty much have the same standard. AASHTO is for transportation. ASTM is for more of like international. It's for a little bit more of the private sector. It's not just in the transportation world. So the mixture design, so how much your weight, so how much you're actually designing is in this column, and then how much you're actually going to batch. So your batch weight is over here. So you can see, you have your water, which you may have 267 pounds of water or 32 gallons. And then you just multiply it by in essence 10 to get these numbers. So some of the basics, like I was communicating, the concrete standards, ASTM and AASHTO, again, they're very similar, going to communicate the materials, the testing, the practice of how to do something. So whether it's there's a standard for aggregates, there's a standard for ready mix concrete, cement, flash, whatever it is, there's a standard for it. There's also a standard way that you're supposed to test, to conduct a test. So there's a standard way so that you don't have less test variability. And then there's also like practices. So things like how to go out and sample, concrete or aggregates. There's a practice. And it's also important to kind of realize that ASTMs are not just in the construction industry, but I think you can even find an ASTM on how to push a broom, how to sweep properly. I've seen them on the back of ketchup packets every once in a while. So, it's ASTMs, is more international and it's a lot more broad. AASHTO is just for transportation work, really. All the state DOTs come together and they develop standards. I've actually wrote AASHTO standards and then had a DOT committee we'll do your team members on it, actually go and submit it and go through the whole process and approve my standard that I wrote. So it's pretty cool to see that process and how it unfolds. ASTM, they have a very similar one where they have committees, just like AASHTO, but their committees are a little bit more. They're not just transportation, but they're kind of a little bit of everybody, and they try to make it where it's a really good blend. I used to be on some of the committees for ASTM 04.02 for concrete aggregates, and go through as a main voting member. And then I was on different subcommittees. And so it was kind of interesting to see how people were trying to change the standards, and usually in a good way. People really do want to do good things, not in a bad way, but usually they want to improve the standards. So some of them were very creative in how they were trying to reword stuff so that it made more sense for today, or maybe a technology change, stuff like that. You also have, in general, you have ACI. So American Concrete Institute is an international global organization that produces documents. I'm actually on ACI 302, construction of floor slabs, ACI 211, which is mixture proportioning of concrete, and then I'm also on ACI 309, consolidation of concrete. In each of these committees, I named off 3 that I'm on, but there's for sure over 50. I forget how many off the top of my head committees that are, in essence, they're people that are specialized in certain parts of concrete. Believe it or not, there are well over 50 different committees that are specialized in different parts of concrete. So you think that concrete's pretty basic, but it's really not. It can be pretty complex. And there's a lot of good specifications and guides and other things out there. ACI more focuses on building codes and stuff like that, like 318, 301, or specifications for concrete, for building concrete. And some of these other ASTM and AASHTO, they're not building codes necessarily, but they're more of the standards for the materials or the testing or the practice. So ACI a lot of times will reference and say, hey, you need this type of cement or this type of aggregate to meet these, this ASTM or this AASHTO specification. So just kind of be aware. So ACI is more of an engineering thing, and then ASTM and AASHTO are more of, you can even think of it more of like a materials engineering, more of a supplier and testing company type standards. So there's some pretty big differences. So ASTM is the American Society for Testing and Materials. AASHTO has changed a little bit their name, but it's currently it's the American Association of State Highway and Transportation Officials. One thing I probably didn't already mention was that these standards are usually updated yearly. Some of them are just grammar errors. Some of them are a little bit bigger. It just depends on what you're talking about. Each of the standard is reviewed every 4 years. So you have to have a good, thorough review every 4 years by the committee. So whenever you look at AASHTO standards, you're going to see AASHTO, and then there's going to be a blank, and then a bunch of numbers, and then dash a year maybe. There may be a year behind that. So you may have AASHTO, and then right behind that you're going to have a letter. So M's for the material specification, T's for the testing standard, R is actually for practice. And then if you have, say, like an MP or a TP or an RP, those are actually provisional standards, meaning we just wrote a standard and the standard may actually change some. It's temporary, really. We're going to just test it out, and so it may change quite a bit over the first few years just to kind of make sure the standard makes sense. And then right after that letter or two letters, you're going to have a standard number. That standard number is whatever that committee assigns to it. So it could be, if it's 80, if it's M85 for cement, that 85, it was just what AASHTO and the AASHTO committee, it's just the number that was provided. And then if you see a dash and say it's, 20, then that's the year that it was published, so 2020. With ASTM, they do their stuff kind of similar. The very first letter is actually, a lot of times you're going to see a C for cementitious, ceramic, concrete, masonry type materials. Sometimes you'll see like a D on some of the stuff because it's kind of miscellaneous materials or products. So sometimes you'll see for a practice, you might see a D every once in a while, but most of it's going to be a C. And then right after that, again, just like AASHTO, the ASTM, they're going to have a standard. It's whatever that standard number it is. So ASTM C150 is, the standard for Portland cement. And that 150 is just what was given from the committee. Then you're going to see a dash, and just like AASHTO, there's going to be a year. So if it's 20, it's, year 2020. If it says 15, it's year 2015. So to kind of help the confusion between ASTM and AASHTO, I put together this table. A few years back, they actually had a big court case where people were saying they couldn't merge because they were trying to merge these standards kind of together, where they wanted to be separate organizations, but just use the same standard because there's so much redundancy, and the courts communicated that they could not. So now they've kind of backed away, and ASTM or AASHTO have been making their own standards from that. So just kind of recognize that. All right. So this is kind of a good table to kind of help for just materials in general for concrete and aggregates. So you can kind of see what the ASTM is or the AASHTO for it. And so for cement, let's kind of talk about cement for a minute. So basics of cement, we'll go through, I should say before I start, we'll go through each of these materials in an individual lecture. So we'll have a lecture over cement, we'll have a lecture over fly ash, a lecture over water, a lecture over coarse aggregate, a lecture over fine aggregate, and that's right, a lecture over admixtures. So just kind of the basics about cement is that gray powder that goes into concrete. You take a bunch of limestone, sand, and clay. You put it into this gigantic oven called a kiln. It melts down into in essence lava. So it's like a man-made volcano inside this gigantic oven, this gigantic kiln that's really, really hot, 2,700 degrees. And eventually by the end of it, it actually cools down. This oven again turns in a certain way at a certain slope, and by the end of it, by the end of your clinker cooler, that it looks like little bitty clinker balls is what they're called, and this little gray spherical ball can be actually ground up into cement. So it's really cool, how it gets put through this plant, and it makes cement. We'll talk about how that kind of works here in a little bit. So when we talk Portland cements, there are 5 different types. In general, type 1 and type 2 are the most commonly used cements in the United States. A type 1-2 is probably the product that I see most commonly used in the United States, which really is a type 2 cement that meets the standards for a type 1. So a lot of engineering standards will say, for this project, I need a type 1 cement. Well, they really produce a type 2 cement and a type 1 cement. The cement meets both standards, so they'll just put type 1-2. So it's really common, and a lot of the difference between a type 1 and a type 2 deals with the C3A content. The C3A in cement can actually, you need to you reduce it. So if it's above 8%, it's a type 1. If it's between 5 and 8, it's going to be a type 2 cement. And then if it's below 5%, if it's 5% or below, then it can be a type 5 cement. And this C3A actually can react with sulfates, like if they're in your soils, and cause sulfate attack where you have cracking and erosion of the concrete. So it's not a good thing to if you have sulfates in your soils. Now C3A is there's a lot of great things, a lot of great attributes about it, with strength and setting time and such. And but you just got to be kind of realize that if you have sulfates in your soil, it may be asked to have a type 2 cement. Type 3 cement, what that is it's high early age strength. So it's usually a type 1 or a type 2 cement, and they just grind it even finer. So they have more surface area, it reacts faster, and you can get those higher early strengths up front. But you know what the negative is you're not going to get as high strengths further on down the road. A type 4 cement, low heat of hydration, that's actually it was built for the Hoover Dam. That's the reason why type 4 cement was developed. They really didn't use it a lot on other projects after that. And so now you can just really use a type 2 cement with fly ash replacement. So class F fly ash, usually at 25-30% replacement, usually does a pretty good job of low heat of hydration. I should also point out with a type 5 cement, right here with the high sulfate resistant, that there's probably, I believe, 8 plants in the United States that actually can make a type 5. A lot of them don't. And out of those 8, I think maybe 3 have made a type 5 in the last 5 years. So there's not a lot that are capable of making a type 5 cement. So what they'll do is they'll take a type 2 with a class F fly ash usually, or sometimes even a class C, and they'll just do some testing to see how sulfate resistant it is. So in Oklahoma, again, most of the cements are going to be a type 1-2, meaning it meets the requirements of both a type 1 and a type 2. That's the most common in Oklahoma. A type 3, there's a couple plants that make a type 3 cement, so high early age cement. This is typically going to be used in your precast facilities, pre-stress facilities. You may see it every once in a while on they don't do a lot of high-rise buildings, but you may see it on that, but not normally in Oklahoma. You just see it on other places in the United States that have more type 3 cement. Again, type 4, it's just not made. Use a type 2 with fly ash. And then a type 5, it is possible to maybe get it. I think Ash Grove Cement up in Chanute has made a type 5 cement in the last 5 years. Bootsy Cement over in Maryville, Texas, which is kind of by Sweetwater. They have made a type 5, but it's just not as they redid their plant, and so they actually, I think their oil well cement technically meets a type 5, but it's better to just really, from what I understand, is neither one of them, unless they've changed their you know, their fillings. They really don't want to have a type 5 cement in their silos. They'd rather just sell you a type 2, and then just have, you know, and then use fly ash and do some testing with it, because it really messes with their silo spaces. But they could change. Okay, so I'm not, you know, I'm not their advocate. I don't represent either one of those companies. So, you know, but that is what has been communicated just in the last couple of years for sure. But they may, you know, they may open up and make a type 5, but I doubt if they will. It's just not used very much. There's really just a few cement plants that make it. We talk about fly ash. Fly ash is actually a byproduct of the coal power industry. So whenever you go and your electricity at your house, it's actually put through a furnace. That coal gets burned up, and you have two types, and it generates, you know, it has steam that gets the output that generates the turbines. Well, that's great and everything, but this coal that gets, you know, it's combusted, gets burned up. You actually have you have two different things that are happening. You have your bottom ash, and then you have fly ash. So if you ever went out maybe with a brush pile and you burnt some, you know, some limbs and stuff, it's very clear whenever you watch that brush pile go up. There's some that, you know, a lot of that ash is on the bottom. It's on the ground, and then there's also ash that flies upward. That's literally what this is. The bottom ash, you know, just it's heavier, it flies down, and then the fly ash goes upward, and it gets caught into precipitators. They have funnels and everything, so it just doesn't just go out the smokestack. They collect it all, and they say, "Oh my gosh, what are we going to do with all this, you know, ash that flew up in the air?" Well, we're going to call it fly ash, and let's see how good it works in concrete. And they found out it worked really well. You could actually take out a little bit of Portland cement, and you could add, you know, fly ash. And the same thing happened actually with slag. So slag's from the steel industry, and what they said was, aha, I can take this slag, you know, this byproduct from the steel industry. I can take it, I can regrind it, and then I can put it in concrete, and it works really well. And it's, you know, and both fly ash and slag are normally a lot more economically cheaper than cement. Cement's usually one of the highest ingredients because you're fully manufacturing it. Silica fume is actually from the silicone computer industry. And it's a byproduct too. And so very similar to what you think of with fly ash. And so they'll just collect it all. And this silica is very microfine, really small particles. And they'll take all this, these different SCMs, and they've used them in concrete. So normally you just have one SCM. You usually have a fly ash. Either it's two different classes, either class C or class F, based on the calcium content of them. And then so in that the differences mainly are how they react, how they perform in concrete. And so for fly ash, usually between 10 and 30%, 10 and 35% replacement is really common. So you're literally, you know, say it's 10% replacement. So you're going to take, so in general, you know, if it's 100% Portland cement mix and you want to replace 10% with fly ash, you're going to take out 10% of the cement and you're going to add 10% of fly ash. That's kind of what the replacement value is about. So your mix is really, you know, the result is you have 90% Portland cement and 10% fly ash. So together it's still 100% cementitious materials, but that's kind of the difference. And that does save you some money for your concrete, and it does produce it can improve the properties, the performance properties of your concrete, whether it's durability or workability. It can improve it. Water is something that's sometimes overlooked. You really don't want to use super dirty water. You want to use something that you can drink. So most public water sources are going to be used without needing to be tested. Recycled or questionable water, it really needs to be tested and approved. So, you need to go out. If there's anything you wouldn't drink, or if it's recyclable water, you really need to go out and test it, make sure everything's going to look fine. You don't want oils, salts, acids, alkalis, organics, anything that's going to change the strength of your concrete, change the area of your concrete, the workability. If you really want something that is going to be pretty low maintenance. So you kind of have to be careful when you talk about recycled water, and you have to have kind of a system in place. Usually when you talk about water, people focus a lot on the water to cement ratio. So how much water do you have compared to the amount of cement, that you have in that concrete. So it's kind of like if you think about painting and, you do whitewashing, you whitewash. So if you keep adding water to your paint can, you can get more and more paint out of it. But eventually you get to a certain point where, it's really water that you're painting on that, say that fence, that you're painting on that wall or whatever you're doing. And so you don't obviously want water. And so it just depends on how, what degree of whitewashing do you kind of want whenever you're painting. So that's kind of what you're doing with cement. The more water you add, the more you're diluting your cement, so it has less and less impact. So you're going to have lower strengths normally, and it's going to change your setting time, and you could even have cracking issues because the concrete's not going to have those good internal stresses. So a lot of times now, instead of calling it a water cement ratio, they call it the water to cementitious material ratio. Either one, they're kind of interchangeable. But just realize that cementitious materials, it's going to be the cement, the fly ash, the slag, the silica fume, etc. And this ratio is done by weight. So the weight of water divided by the weight of your cement and slag, fly ash, everything that's used in that specific mix. That is your water cement ratio. So it's by weight. So how that kind of looks when we talked about whitewashing and painting and stuff, if you have less cement and more water, your particles are going to be farther apart. Your cement particles are in the water solution. And so over time, because it's a chemical reaction between cement and water, they're going to produce product on the outside, and they're going to have a harder time to connect. It's going to take longer. These bonds to connect all these particles together with these products it's going to take a lot longer to get to initial set and final set. And then over time, your strengths are just going to be weaker because it takes a lot more to extend to get that bond from the cement particles. And if you have a tighter bond, like you see here, it's going to be easier to bridge to get to these cement particles, and you'll have a much tighter matrix, a much tighter pore structure of your concrete. So we talk about aggregate, again, coarse aggregate, fine aggregate. They make up over 60% of the concrete. I've seen some where it's actually up to 90%. You really want, you have your coarse aggregate here, you have your fine aggregate here. You really want this wall to be built up higher so that you don't get contamination, because you want coarse rock whenever you take a scoop with a front end loader. You don't want, coarse aggregate with a little fine aggregate in it. So, just kind of be aware of that. An aggregate is a huge deal. Not only does it make up, 60 to, like I said, 80, 90% of the volume of the concrete, but like you see here with the aggregate gradation, I'm going to show you 5 mixes, and the only thing I'm doing differently is I'm changing up the rock and the sand, changing the gradation. So it's the same amount of cement, same amount of water, same amount of admixture. Only thing I'm changing is the aggregates, how they're proportioned. And so this exercise kind of explained to you how important aggregates are and the gradation. So this is a basic moderate amount of both rock and sand, and so this is for a 5-inch slump. You can pump with it for a bridge deck. You can use it for a floor slab. It's a very typical mix. And I use the slump test here because that's the most commonly used test to kind of communicate the workability of concrete. So this is a 5-inch slump here. It's a very good mix. If you have, and so what I did was I took out some rock, put in some sand, put in a lot of sand. And if you have too much sand, what a lot means, if you have too much, then you're going to get a nice stiff mix that's actually not only stiff, but it's sticky, and it'll stick to everything. So it went from being a 5-inch slump to I think it's down here at like a 2-inch slump. So again, only thing I did, they're completely different workabilities. This is great for floor slabs. This is not. You may not even want to pave with this, even though it is a 2-inch slump. You may not even want to pave because it's so sticky. You also have a high intermediates. We have a bunch of 3/8-inch chip put in there. So you take out a little bit of rock, you put a little 3/8-inch chip, like a little intermediate, and all of a sudden it's stiff too. So it's not sticky like the sand, but it's really stiff. And so this is actually more of like a 2.5, 3-inch slump. If you don't have enough sand, if I take out a lot of the sand and I put in a lot more coarse rock, you're going to get something that looks like a bunch of rocks covered in paste. So this is a 7.5-inch slump, but the cohesion looks absolutely horrible. And then if you take out and you add more coarse rock and you take out some of the, and you don't have enough, you just keep adding more and more rock to it, you're going to get to a point, and you may have enough sand, but you have way too much rock. What's going to happen is you're going to get a lot of segregation, and these rock particles will just kind of want to separate. There's just too many of them. So you kind of need almost like a well-graded distribution of aggregates almost. And what that well-graded kind of defines, I think of the tarantula curve that I developed, and that kind of helps to kind of communicate where some of that's at. And we'll talk more about the tarantula and stuff in a later class. So the last thing is admixture. So it's very common to use air entrainment for freeze-thaw durability. You may also use a mid-range water reducer to improve your strengths and your workability, mainly your workability, and it will increase your strengths normally too. So chemical additives are usually either chemical additives, is what I'm referring to. So you have powdered or liquid form. And these additives are usually added to improve the workability of the concrete. That's what they're incorporated for. Powdered dosages are usually percent by weight. Liquid dosages are in fluid ounces. So ounces per CWT, that actually means 100 pounds or ounces per 100 pounds of cementitious material. So that kind of helps. So if it's 4 ounces per hundredweight is what it's referred to, that means there's 4 ounces per every 100 pounds of cement in that mix. So if you have 400 pounds of cement or cementitious material, then you're proportioning based off of 4 ounces per hundredweight, then that means that you're going to have at least 16 ounces per yard in your mix. So 4 times 4. Again, for ASTM C494, chemical admixtures, there are a variety of different types. There's even a type S that I don't know why I left off, but it's down here also. So type A, type D, type E, F, and G are all water reducers. Some also are accelerators or retarder. And then other ones like a type F and a type G, those actually drastically improve the workability of the concrete even farther than just a type A, D, or E. So they are, type F or type G. You also have a type B or type C that's just an accelerator or just a retarder. So they may be a combination of a water reducer and a retarder or an accelerator, or they may just be one, they may just be a water reducer or an accelerator. So if you think about like a super plasticizer, that is very similar to a high range, that is a same thing as a high range water reducer. So, or a plasticizer, super plasticizer, super P, those are all the same terminology. And they are technically all water reducers, but this is more focused. The type A, D, and E are more of like what you think of as like a normal or a mid-range, where they have, more of a slight to a moderate workability improvement, as opposed to like a type F or G, which have a major change. They go from being, such as like, for example, a really stiff 2-inch slump mix to you add, say, 4 inches or 4 ounces of a high range water reducer, or and all of a sudden you're at an 8-inch slump. And so it's extremely flowable difference. And so that's kind of what I'm communicating. So one last little brain teaser is people, they always talk about Roman concrete. Is it really better than modern day concrete? Have all this technology, but can we really make concrete better than the Romans? Well, I think you need to understand there's a lot of different answers. The only really well-built Roman structures are still here. The Roman concrete had much lighter live loads. And a lot of times they weren't even allowed to use those roads for 180 days after they were built. So you can even, most of their heavy equipment was, foot traffic. It was wagons and horses and stuff like that. And so, a lot lighter than like an 18-wheeler you think of today. Good morning. I'll put my helmet on.